trying to share the screen here. Can you see my screen?
Yes, yes.
And you can hear me?
Yeah.
So everything looks okay.
Let me start the recording. Yeah. Yeah, maybe in this way you can start.
Yeah, fine. Is it okay, Sudhir? Everything done?
Yeah, I think it's okay.
Yeah,
it's okay.
okay. So anyway, let us formally welcome the speaker for today. It's my pleasure to welcome Professor Sudhir Ghorpade. He is at IIT Bombay, professor, and from where I have superannuated. So it's a pleasure to at least see him online. I have not visited IIT for 3 years, so it's a pleasure to see him online at least. Yeah. And I have already shared the link for his profile where his achievements are available online. You can have a look at that later on. So let me welcome him to the session for today for Math Clinic. Professor Sudhir, you can start.
Okay. So thank you very much. As Professor Rana said, he's my colleague, and I have known him for many years, and it is my pleasure to lecture in this very nice activity which he has begun for some years. I see that there have already been several nice talks. When he asked me to give a lecture, I was thinking of speaking on some other topic, but he specifically said that maybe I should speak something about coding theory. So I decided to make this talk. So let me, I'm going to say a little bit about the first part of the title, which is Mathematics of Digital Transmission. And just by sort of pointing out that, we often say that we live in this digital world and so on and so forth. Sometimes without realizing that what is behind that is mathematics. I mean, you go to a movie theater, you see there is some sign saying digital Dolby music or something like that. We use mobile phones, we use CD players, DVD in our day-to-day communications and so on. And there is a whole lot of mathematics which actually is happening in the background. And I sort of want to highlight some of that mathematics here. So when that digital Dolby music, you're probably not thinking about mathematics, but digital has to do with digits, which are something which one first learns in mathematics. The digits in the case of like digital transmissions and so on are often binary digits like zeros and ones. So when one says that lots of things are digital, which means your music, your data, your images, your communication, etc. What that means is that whatever that data is, it's sort of converted into a huge stream of maybe zeros and ones, and that is what is communicated across, and that's where the digital communication takes place. So you can very well imagine converting numbers to some binary form. You can take you can write our English language. There's a finite alphabet set, add to that some characters, etc. You would still have it's like a huge string of things coming from that finite set, and which can also be digitized. So lots of things can be digitized. So let me say a few words about the origins or genesis of coding theory. I have to warn you that I'm a mathematician, and a lot of what I'm going to speak will be mathematics. Do you see the thing? Okay, I don't see my. I want.
Yeah, I think there is some internet issue.
Hi.
Yes, sir.
Sorry, I think there was a network problem. I just switched to my mobile. Okay, so you can see me again.
Yeah, we can hear you now.
Again, sorry about that interruption. So what I was saying is that a lot of data that is used for communications is often in the form of digital message, and the problem of information transmission is usually to send this data across what is typically what is classically called a noisy channel. Okay, so so I mean, I'll just show you a picture. I'll come back to this slide. So your message could come. You may have some message which may come from a message space. So this message, and this message could be some string of 0, 1. Okay. So this is a mathematically what you're saying is this is something which belongs to the set of k tuples of some alphabet set. Here I have taken q to be 0 and 1. Okay, so maybe this is your message, and what you want to do is let's say you want to send it across. Of course, in practice, your message is like a string of maybe million bits or something like that. Okay, and what may typically happen is that when you send across this message, maybe one of the 0 becomes 1, and maybe you have a 1 here. Okay, instead of the 0. Okay, so you have an error, and the idea of coding theory is to instead of sending this message across what they call noisy channel, you encode that message into a potentially a longer string in such a way that when you send that across, even if there are errors, they can be detected and more often than not corrected. Okay, so so here is maybe, I mean, so maybe you have a message, let's say M maybe, and you want to send it, and this is the received message here. So this will, if you just send it directly, it will kind of tilt it. It will introduce errors. So what coding theory tries to do is you encode that message into something that are called code word, and you send that across. Okay. Then you have the received code word, and then you can and then you can try to decode, and you would then get something which is typically much closer to the original message than what it would have happened otherwise. Okay, so we are going to be really concerned with this this process here of taking a message and encoding it into a code word. So that's what is shown here. So this is a message space. Here is the encoder which changes it to n bit. This is a picture I have taken from the internet, one of the ResearchGate papers. And you send it across, and then you decode and hopefully get back the original message. It's a very simple idea in some sense, but it leads to profound number of applications, And this is something which kind of a person who is called the originator of coding theory is a person called Claude Shannon. So he wrote a paper in the late 40s on the problem of information theory, and he showed that you can by coding suitably, you can correct errors up to sort of desired epsilon, and that, so to speak, started the field of coding theory. So I'll go back again to my general slide where I have tried to explain the genesis in words. So the problem of information transmission is sort of solved by taking a message, which, as I told you, is like an element of q to the power k, where q is a finite set, for example, 0 and 1, and mapping it to a much larger set like q to the n, where n is typically significantly larger than k. And you do this mapping in a clever way, so that instead of sending this element of q to the k, you send a corresponding element of q to the power n. Okay. In other words, you send the elements which are in the image of this map, and these are these elements of the image. They are what are called code words. Okay. So and because they live in this space q to the n of n tuples of elements of q, they are called code words of length n, and together they constitute what is called a code of length n. Okay, and I'll come back to this part, which is sort of more mathematical. In many cases, this finite alphabet set q, just for example 0, 1, has a structure, has an algebraic structure of a field. Right, that field means where you can add, subtract, multiply, and divide. Of course, divide by non-zero. For example, in the set 0, 1, you can declare 1 plus 1 is 0, and 1 into 1 is 1, and of course 0 into anything is 0. And you will see that all the standard axioms of addition, subtraction, multiplication, division are satisfied. This is indeed the smallest field that there is in the world. So in general, Q may be a field with two elements like 0 and 1, or a finite field, and in which case this Q to the K is a vector space of dimension K. Q to the N is a vector space of dimension K, sorry, dimension N. And this map from Q to the K to Q to the N, injective map, it is sort of natural to require that to be linear. So when the encoding is given by linear map, then the resulting code is said to be a linear code. And these are really the most widely studied classes of codes in coding theory. Okay, I'll become more and more mathematical. I just want to mention that if there are any questions or comments, please just unmute yourself and ask questions. I'll be happy to have mathematical interruptions, or if you have comments, if you think I'm too slow or too fast, also do not hesitate to tell me. Okay. All right. So let me sort of give you an outline of what I'm going to do in this lecture. So I want to give you some flavor, some one lecture. Obviously, I cannot tell you all that there is to know in coding theory, but I want to give you some idea of some fundamental notions, some basic result, some important examples, and if you like to learn more, etc., I would mention that there are these two standard references. One is an old book of Florence J.C. McWilliams and Neil Sloan called The Theory of Error Correcting Code. This is a pretty fat book. I think it's about 700, 800 pages or so. I sometimes called it jokingly the Old Testament. It used to be one of the most standard references. And then there is a newer book, which is called Handbook of Coding Theory, which is actually edited by Veraplas and Huffman. And in fact, it has articles by several leading experts on various aspects of coding theory, beginning with an introduction. So if that was about 800 pages, this handbook is, I think, over 2000 pages. So sometimes I call it the New Testament. So if you really want to learn about coding theory, then you should really read these books. Of course, there are many other books in the market that you can find. Van Lint, Justison and Holt, Ling and Singh, etc. Fassman, Ladut and Nogin have a book of which the second volume came not too long ago. I myself have a small set of notes, nowhere close to 800 pages, maybe not even, maybe 20, 30 pages, something like that, based on some lectures I give. You can find them on my homepage. So this is my homepage, which you can get by Googling my name, for example, and you can find a lot of information, in particular notes of lectures that you can get by just browsing on that page. What is it that I'm going to assume in this lecture? The mathematical prerequisite. I would like you to have some familiarity with finite fields and linear algebra. I think linear algebra is something that most people here would be familiar with. Finite fields, several of you would be familiar with. So I want to just begin with one slide on finite fields to tell you what they are. So here is that. So this is one picture I want to show you of a great guy. This is finite fields. They are also known as Galois fields. So what is a finite field? Finite field is simply a field with finitely many elements. So let's say something with 2 elements, 4 elements, 9 elements, etc. And it's a basic result that you can construct a field with q elements if and only if q is a power of a prime number. So most likely you are familiar with a field with p elements where p is a prime number, that's z mod pz, and or integers modulo p, or residue classes of integers modulo prime number p. That's a field with p elements. And it turns out that you can construct field more generally with elements which are a power of a prime number, like p to the power e. And up to isomorphism, there is basically only one field with given prime power elements. So these were actually first studied by Everest Galois, whose name you may have heard in various contexts, theory of equations, Galois theory, and so on and so forth. As you can see, he lived a very short but eventful life. Died before he was even 21 years old in a duel, actually. And he wrote a paper which was published in 1830 called Sur la théorie de nombre, on number theory, which is where the finite fields appeared for the first time. And I like to give this, of course, that is fairly well known that Galois introduced finite fields. What is perhaps not so well known is that what I think is the second most important theorem in finite fields is one written by a pioneering American mathematician called E.H. Moore. Some of you might have heard his name. And it's interesting where his paper is published, because most of us probably went to school in India or grew up here and would have heard about Swami Vivekananda going to Chicago and dazzling the world with his brilliant speech. So there was the Chicago World Fair actually in 1893. And what is not so well known, or certainly not taught to us in school, is that the Chicago World Fair also had a mathematics component, and the mathematical congress there contains, the proceedings contain this paper of E.H. Moore, which I like to call the second most important paper on finite fields. Anyway, that's just an aside. So, so I'm going to use this notation FQ to denote a finite field with q elements. If you're not very comfortable with general finite fields, you can just take q equal to 2 or q a prime. But really speaking, you just think of FQ as a field with q elements, and as I said, it is essentially unique, and that's why I have this notation. Other notation people use, especially in finite geometry, GFQ. GF stands for Galois field with q elements. Okay, all right. So let's get started. In fact, in the first instance, I'm not even going to get into linear codes. Just talk about codes in general. So what is it? So I have just start with an absolutely arbitrary finite set. I'll call it capital Q. Okay, and I'm going to denote the cardinality of that by little q. So what is a code? So Q to the N is the n-dimensional space coming from the alphabet set Q. In other words, set of ordered n tuples of elements of Q. A code of length n is simply going to be a subset of Q to the power n. Nothing could be simpler than this definition. So that's what it is. And the size of that is just the cardinality. Mod C denotes the cardinality. And it's customary to call the log to the base Q of that size as the dimension of the code. Okay, you will see why I call it the dimension of the code. Well, now on this space Q to the N, you can think of it as like an n-dimensional space. For example, the room that you are sitting in is a 3-dimensional thing, and you can think about, but it's sort of discrete because each of your axis has only finitely many possible coordinates. So, but you have this n-dimensional space, and you have this code C sitting inside there. So some bunch of points in your 3-dimensional room, if you like. And what kind of distance function you have in this discrete n-dimensional space? It's a very simple-minded distance, which is named after Richard Hamming, another pioneer of coding theory. It is the following, that if you take two elements, say x and y, which are n tuples, x1 to xn, y1 to yn, distance between them is defined as the number of positions in which x differs from y. So if the first coordinate, third coordinate, and the seventh coordinate of x and y are different, and all other coordinates are the same, you say distance is 3. Okay. If x is equal to y, none of the coordinates are different, then distance is 0. So in fact, it is clear that d of xy will be 0 if and only if x is equal to y. It's also clear that d of xy is greater than or equal to 0. And with a little bit of effort, you can check the triangle inequality. So this is a metric, and this is a distance function, and that's called the Hamming distance. Okay. So even already with that simple notion, we can define an important concept called minimum distance. So minimum distance of a code, which is typically denoted by d of c, is defined as the minimum of the distances between distinct elements of the code. So you, again, as I said, you think of your code as some bunch of points, lots of, maybe millions of them, sitting in this n-dimensional space, if you like, your 3-dimensional room, but a discrete version of that. And the minimum distance of that bunch of points, that code C here, is just the minimum of distances between any two distinct elements. Okay. Obviously, you should not take x equal to y, because then dxy will be 0, and that would be the minimum. Okay. So you take different points, you measure the distance between them. It will be some number from 1 to n, and you take the least of that. Okay. Now there is a simple bound that this minimum distance has to satisfy. Okay. I'll come to that, but before that, I will tell you what makes something a good code. So what would make something a good code is a subset C for which so C is good if minimum distance is large. Okay. In other words, you kind of want to pack this n-dimensional space with subset C so that the points are as far apart from each other as possible, and still there are sufficiently many points. So that's the sort of game you're playing. Okay. Why do you want it to be large? Because the general thing is that if minimum distance is D, then C can correct up to D minus 1/2 errors. Okay, or maybe integer parts. Okay, it's not difficult to show. This is not the thing I'm getting into. This is related to what is called syndrome decoding. So therefore, if you want to correct more errors, you want this minimum distance to be large. Okay, so naturally, so what you want if DC is large, and also the size is large, because otherwise, I mean, it's possible to sort of make DC to be large if I just make C to be consist of just 2 points, which are which differ from each other in all the coordinates. And but then you have just two code words, and that's very few, because let's say when you want to encode a message space which has lots of messages, you cannot just get an injective map into a space consisting of just two code words. So you want the size of C to be large, but at the same time, you want the minimum distance to be large. So that's the kind of game that comes into picture when you want to sort of construct good codes. There are other parameters of something is a good code. We will come to that. So, so let's say, okay. So this singleton bound kind of tells you that suppose I have a query code. Query code means an alphabet set of cardinality q of length n, so subset of q to the n, and suppose its minimum distance is some given number d. Okay, then it says that the maximum size of the code that you can construct with that minimum distance is at most q to the power n minus d plus 1. Okay, I translate this result in another way. In other words, if so this AQND is like the max of cardinality of C, where distance of C, minimum distance of C is d, and C is contained in q to the n. Okay, so so if k were to denote the dimension of C, remember that's like log to the base q of cardinality of C. Then this power of q will go away. You sort of take log both sides. You will get this is same thing as saying k less than or equal to n minus d plus 1. Or you can put it another way. This is same thing as saying d is less than or equal to n minus k plus 1. So that's called a singleton bound. And they say that every lecture should contain at least one proof. I may have more than one proofs because otherwise there is no fun. So this is just a one-line proof of this result, so which will help you understand this. So let us see. So suppose I have a code C whose minimum distance is d. Okay, what can I do? I can take my C, which is living inside q to the power n, and I project it onto q to the n minus d plus 1. What do? I take a code word, say x1 to xn, and I take a code word, and I just forget the first d minus 1 coordinate. So I look at xd to xn. Okay, so I'm therefore I land up in this space q to the power n minus d plus 1, and I claim that this map must be injective. That is 1, 1. Why is that? Because what is an injective map? Yeah, is there a question, Mr. Mani? Hello. Okay, if there is a question, please unmute and ask, or you can type in the chat box. I'll try to monitor the chat.
Excuse me, sir.
Yeah. Yes.
What is meant by injective?
Injective means 1, 1.
What do you mean by that?
What I mean by that, I'll explain. Injective means it means if x is not equal to y, then fx is not equal to fy. That means distinct points go to distinct points. Such a map is called a 1, 1 map or an injective map. Okay.
Okay, thank you.
Somebody has asked what is a kernel. That's the word I have not used here, but I can explain to you a little later. Okay, so now maybe you can tell me why is this map injective? Why do suppose x is not equal to y, and if it were the case that fx is equal to fy, what is fx? Fx is going to be this this thing xd to xn. So f of y will be yd to y. So I have two code words x and y. X is not equal to y, where xd to xn and yd to yn are equal, which means x and y differ only in the first d minus 1 coordinates, which means the distance between them, the Hamming distance between them, is at most d minus 1. But d was the minimum distance, remember? D was the minimum distance. It's the minimum of distances between any two distinct points. So if two points have distance between them d minus 1 or less, they have to be equal. So x would have to be equal to y, which is a contradiction, because I started by saying x is not equal to y. So that shows this map is 1, 1, and therefore I have a 1-to-1 map from C to this space. I can use a different color maybe here. And that means the cardinality of C is at most the cardinality of this image, which is q to the power n minus d plus 1. And that exactly proves what I wanted to show here. The maximum size of a code of minimum distance d is bounded on the above by q to the power n minus d plus 1. I hope this proof is clear. If not, maybe the slides will be available. You can think about it. Okay. So with your permission, now I want to go to linear codes. Okay. So what I said so far was about an arbitrary code where just a subset of q to the n. Now I'm going to take my alphabet set q to be fq, the finite field with q elements. Okay. So then query linear code is just not just a subset C, but a subspace of this vector space. Okay, this is an n-dimensional vector space. Any subspace of that, that's called a linear code of length n, or a query linear code of length n. Okay. Yeah, is there a question?
You use.
Is there a question?
No, I think. Yeah.
All right. Let me define a few more notions. So now you will see that suppose the dimension of this code, linear code, where k, dimension of C is equal to k, then the cardinality of C, because this is a dimension over this finite field fq, will be q to the power k. And so then k therefore becomes like log to the base q of the size of C. That's why when even in the setting of general nonlinear codes, we call log to the base q of cardinality of C to be the dimension. So here it actually, that notion of dimension coincides with the usual notion of dimension in linear algebra. So if I have a query linear code of length n and dimension k, okay, I would like to sort of explain to you that the minimum distance of that can be alternatively, see earlier what was this? This was the minimum of the distance between x and y, x not equal to y, and x and y in C. Okay, but distance between x and y is, if you think about it, is the number of positions where x and y differ. It is exactly what is called the Hamming weight or the support weight of x minus y. What is the Hamming weight of a vector? It's just the number of positions where you have a non-zero coordinate. So in general, for any vector x, Hamming weight of x is number of positions I for which xi is not equal to 0. And the set of those positions is called the support of that vector x. So the minimum, so this Hamming distance between x and y will become the, the Hamming weight of x minus y. And therefore, if you think about it, because x and y are in C, C is a subspace, x minus y will also be in C. And to say x not equal to y just means x minus y is not equal to 0. So really, the minimum distance then becomes the minimum of the Hamming weights of non-zero code words, non-zero elements of C. That's called the minimum. That's another way to think about it. There is a more general notion of support and Hamming weight of a subcode. Subcode means a subspace of C. And I'll just quickly go over it. If you don't immediately follow, that's fine. It's the support of a subcode D is the number of positions I for which there exists some element in D with a non-zero coordinate in that position. And support weight or the Hamming weight of a subcode is the cardinality of its support. And there is a generalization of minimum distance called the generalized Hamming weight. It is defined as the minimum of the support weights of r-dimensional subcodes of the given code. Okay, and there is a notion of non-degenerate code. See here, the notion of distance is extremely coordinate dependent. So here, non-degenerate would mean that C is not contained in a coordinate hyperplane of fq to the power n. That means, for example, it doesn't happen that the last coordinate is always 0 or the 7th coordinate is always 0, because if that is the case, you might as well forget about that and get yourself a code of smaller length. Okay, so if that does not happen, that code is said to be non-degenerate. And if you think about it for a minute, you will see that this is the same thing as saying here typically R is going from 1 to K. This is the same thing as saying that the last generalized Hamming weight is equal to N. Okay. All right. Already I would like to, I told you that code is good if this minimum distance is large. Okay. So there's a very important class of codes which is optimal in some sense. These are called MDS codes. Okay, so what does MDS stand for? It stands for maximum distance separable, but people hardly ever use this full form. They just say MDS, maximum distance separable code. So, by the way, I'm going to use this notation NKQ code. That means a linear code of length n, dimension k, over the finite field with q elements. So this just means C is a k-dimensional subspace of fq to the power n. Okay. That's called an MDS code if the minimum distance of it meets that singleton bound. That means it is the largest possible that can be for a given code of length n and dimension k. If it is equal to n minus k plus 1, then that code is called a maximum distance separable code or MDS code. Okay, I hope this definition is clear. Here is already a very nice problem, which is actually incredibly okay. So okay, but maybe before that problem, I can ask you a simple exercise. Let's suppose I fix some positive integers k and n, k less than or equal to n. How many codes can there be of length n and dimension k? Now find a formula for number of NKQ codes, number of query codes, linear codes of, sorry? Was there a question? Soumya?
Yeah, someone unmuted, but yeah, Shanmuga, you have some question?
I think, Soumya, you can mute everybody unless you already said unmute only if you want to ask questions.
Yeah, okay.
Okay. Very good. So, that's a nice problem, which is really a question of linear algebra. How many k-dimensional subspaces does the n-dimensional vector space fq to the n have? Okay, it's not difficult, and the answer is known ever since Gauss. I'm not going to tell you, but now let us say in addition to code being of length n and dimension q, I require it to be MDS. That means I require the minimum distance to be this n minus k plus 1. And now you try to find the number of NKQ MDS code, and that's already a problem. Okay, somebody might ask me, what is the difference between a problem and an exercise? So a simple answer is exercise is a problem whose solution I know. A problem is an exercise whose solution I don't know. So really, I mean, this is actually an open problem. Beyond certain special values, nobody really knows what is this exact number. And but you can with some effort solve it for k equal to 1 and k equal to 2. That's not so difficult. So I call that an exercise. So in fact, one of the first research papers I wrote on coding theory was related to this problem way back in 2001. And there was not much progress until a more recent one of some 13 years later. So if you're interested, you could look that up. But I'm not going to get into that details. But I just want to mention that already with simple enough notions, you have some interesting and challenging problems. Okay. Very good. So let me introduce some more notions. I want to tell you that I remember a linear code is like a subspace C of a n-dimensional vector space fq to the power n. So there is a notion of what is called a generator matrix of C. A generator matrix of C is simply a k cross n matrix, so k rows, n columns, in such a way that the rows of that, which are elements of fq to the power n, they form a basis of your code C. Okay. So because C is k-dimensional, so such a matrix, let's say G, is called a generator matrix of code. Because your code has dimension k, the rank of this matrix will be k, and C will be like row vector U times this matrix G, as U runs over arbitrary elements of FQ to the k. Sort of customary in coding theory to think of vectors as row vectors rather than column vectors. Okay, there is a I mean, of course, two matrices can give rise to the same code, and that will happen if and only if they differ from each other upon multiplication by left by a non-singular matrix, and that means they are row equivalent. So there you can take a generator matrix and transform it to reduced row echelon form. So if you require the generator matrix to be in reduced row echelon form, then it would be unique. Okay. A simplest kind of reduced row echelon form that you could get is, because it's rank k, would be you have the identity matrix, so 1 0 0, etc. 0 1 0, and so on, 0 0 1, and something here. Okay, it's a k cross n, k less than or equal to n. So identity matrix and some k cross n minus k random matrix on the right. Okay, that's called a generator matrix in standard form. You can't always do that, but when you can do that, it's particularly nice. Then there is a counterpart of this generator matrix called the parity check matrix. So this is a n minus k cross n matrix, n minus k cross n matrix, such that the code is like it's null space. Somebody asked a short while ago, what is kernel? So kernel is another fancy name for null space. If you are familiar with null space, they are essentially like kernel. So it means that the code consists of those vectors of length n, so that I change that row vector to a column vector, multiply on the left by this n minus k cross n matrix, I get a 0 vector. Okay. So this is a matrix whose rank is n minus k. That's called parity check matrix. And then the terminology is traditional, because when you are over binary field F2, saying something is 0, it's really asking whether that thing is even or odd. So you're determining the parity, you're checking the parity. So parity check matrix. Okay. In general, it's not so easy to write down the parity check matrix given a generator matrix, but if the generator matrix is in standard form, then you can actually write down the parity check matrix also rather easily. Although, by the way, I said though, it's not really unique, a parity check matrix. So if it is in standard form like IKA, then this minus A transpose and identity of n minus k is a parity check matrix for the same code. And this is not difficult to see. I've written down a one-line proof here, but let me not spend time on that. You just have to observe that H times G transpose is 0. Okay, I want to introduce to you one more notion, a very basic notion in coding theory of duality. Okay, so to a code C, you can associate something called its dual. So if this is a code of length n and dimension k, the dual would be a code of length n and dimension n minus k. And how is it defined? It is defined as follows. The dual of a code C, a linear code C, is the set of those vectors y such that the dot product of x and y is 0 for all code words x of C. Okay. And what is this dot product or inner product? It's not really an inner product. It's a bilinear form. So that is given by the usual dot product of x and y is x1 y1 plus x2 y2 plus dot 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 x and y. Okay. So if you take those vectors whose dot product with every element of C 0, that constitutes a subspace of FQ to the power n. It's not difficult to show that its dimension is FQ to the, its dimension is exactly complementary, that is n minus k, and that is therefore a code of length n and dimension n minus k called the dual of C. Okay, I leave it to you if you're interested to show this as an exercise, and also to show that if I take the dual and then again take the dual, I get back the original code. And a slightly more interesting exercise is to show that if your code is MDS, then the dual is also MDS. Okay. I just should warn you that you may have your notions of dual from classical linear algebra, functional analysis, whatever, and you should not. I mean, there is no notion of positive definiteness here. Okay, so it can very well happen, and also C and C perp may not have be essentially disjoint. In fact, it can even happen that C is contained in C per, or even C is equal to C per. Such things are possible. In that case, the code is, if C is contained in C per, the code is called self-orthogonal. If C is equal to C per, it is called self-dual. These are also interesting classes of codes, self-orthogonal and self-dual. Okay. See, by the way, so I mentioned some of the pioneers in coding theory in the first part. They are Shannon and Hamming, and I also mentioned the Old Testament, the book of F.J. McWilliams. So this F.J. McWilliams is a lady called Florence Jessie McWilliams, and she, besides writing that book, proved a lot of beautiful results. And one of them is something which relates what is called the weight distribution of a code and its dual. So before I come to that, let me explain to you what is the weight distribution. You should think of it as something like the kundali or horoscope of the code. Okay, so you are given a code C, length and dimension K. The weight distribution, which is sometimes also called the spectrum, is basically the sequence A0, A1, AN, where what is AI? AI is the number of code words whose Hamming weight is equal to I. Okay, so Hamming weight of everything will be some number between 0 and n. It will be 0 exactly when x is the 0 vector. Otherwise, it is 1 or 2 or 3 or n. Maybe n is some huge number, million. And so you want to know for which weights are there code words of that weight. So that sequence, that's called the weight distribution. And it is customary to, instead of writing the sequence, you write down this polynomial, 2-variable polynomial. This is a way of encoding the sequence, if you like. AI x to the n minus I, y to the power I. This is called the weight enumerator polynomial of the code. Okay, this is another way to write that weight enumerator polynomial. So this is usually denoted by WCXY. Now, a priori, it is not at all clear that if I have a code of length and dimension K, I take its dual. This will have some weight enumerator. The dual will have some weight enumerator. And what is the relation between the two weight enumerators? And a really beautiful relationship was found by this McWilliams, and these are known as McWilliams identities. I'm just going to state them. The way they are derived is so suppose AIs are the weight distributions of C, and BI denotes the weight distribution of C per. Okay, then these AIs and BIs are related by this kind of identities. Okay, this is maybe a little bit involved to explain. So I will translate it in the language of the polynomials. In the language of polynomials, what it says is that suppose you look at the weight enumerator polynomial of C per, the dual. It is related to the weight enumerator polynomial of C by this relation that for x and y, you substitute x plus q minus 1y and x minus y respectively, and you divide by the cardinality of C, which is q to the k. Okay. In particular, if q is equal to 2, then what are we saying? We are saying that W of C per xy is 2 to the minus k. The q minus 1 just becomes 1. So you are substituting x plus y, x minus y for x and y. There are many ways of proving this, but all of them will require more than one lecture. There are ways to relate it to number theory, like Poincare summation formula. There are more elementary ways, but these are somewhat involved. I mentioned to you my set of notes. You can see them for a proof, but just want to mention that this relationship. Okay. Any questions so far? I want to give now some examples of codes to help you understand what are the some codes which come in practice. I'll by and by also tell you about some applications. No questions? Okay. So here are two basic examples of codes. One is in some sense a simple class of codes which goes by the name of simplex codes, and the second one is Hamming code. Okay, so so this is a slightly dense slide. I will explain what is going on here. So I take a positive integer r. Okay, and now then I look at r tuples, fq to the power r. So how many r tuples are there? There are q to the power r. I forget the zero tuple, the tuple which is consisting of all 0. So there are q to the power r minus 1 such non-zero tuples. Then so what I'm going to do is I'm going to write these r tuples as columns of a matrix. Okay, so this is one r tuple, this is the second one, etc. Okay, with the following rule in mind, that if I take one r tuple, say for example 1 0 0 0, then I do not repeat a multiple of that. Okay, so I write all the distinct r tuples which are not proportional to each other, which are not multiples of each other. Put it another way, that I write an r cross n matrix. So how many such will be there? So I have q to the power r minus 1 non-zero tuples. I have to ignore all the q minus 1 non-zero multiples of that. So I just divide that by q minus 1. These many distinct such r tuples I'll have. So that, and that number I have called it n here. Okay. So I write down an r cross n matrix so that no two columns are multiples of each other. In other words, they are linearly independent. They are all non-zero and none of them is multiple of each other. That means any two columns are linearly independent. Okay. So call that matrix HRQ. So this is HRQ. R cross n. Okay. So for any positive integer r, I can write down such a matrix. Okay. So now what is this simplex code? So simplex code. Simplex code is simply the code of length n and dimension r, so that this HRQ is a generator matrix of that. In other words, now I take the rows, which are n tuples, r of them. It is an easy exercise to show that these rows are linearly independent. This matrix is of rank r. And the subspace of fq to the power n that they generate, that is called the simplex code. And I denote it by SRQ, this fancy SRQ. Okay. On the other hand, if I think of that matrix as the parity check matrix of some code, in other words, I look at the code of length n and dimension n minus r with this HRQ as its parity check matrix, then that is denoted by HRQ, and this is called the Hamming code after Richard Hamming. So nice class of code. Okay. It is clear, I think, from the description that these two codes are duals of each other. The dual of HR is SR, and therefore dual of SR is HR. Okay. So if you are interested, here is an exercise for you. You find the minimum distance of this Hamming code and minimum distance of the simplex code. Okay. In fact, for simplex code, you can do even better. You can actually find the weight distribution without too much difficulty. That means the spectrum, and therefore write down the weight enumerator polynomial. Okay. And you will see that the simplex code is actually an example of what is called a constant weight code. That means other than 0, every code word has the same weight, same Hamming weight. Okay. It's a very special type of code. Any questions? Okay. So let me proceed and give you one more very nice and very widely used class of codes, example of code. So so example number 2 or example number 3 is that of Reed-Solomon codes. Okay, these are named after Irving Reed and Gustav Solomon, who introduced them many years ago, I think in the 60s or so. And it's a very, again, a nice simple-minded construction coming from algebra. And it's a one nice way of constructing MDS codes. So let me explain what that is. Okay. So let us take n and k to be any positive integers. N is larger than or equal to k. Is there some question? Is there somebody speaking?
Yeah, no, sir.
Okay. Right. So now what do? I look at polynomials in one variable. So fx is a polynomial in one variable whose degree is strictly less than k. Okay, that means what? F will look like a0 plus a1x, etc. Or maybe I should not use a0. Say c0 plus c1x plus ck minus 1 x to the power k minus 1. Okay, where C0, C1, Ck are elements of FQ. Okay. Now, so that's how I take such polynomials. And now what do? To such a polynomial, I associate an n tuple. I call it C sub f. How do I do that? I evaluate that polynomial at different points. I take point A1, take a point A2. They're all in FQ. I substitute them. So f of A1, f of A2, f of An. Okay. So these are, this is how I define. So this is like an evaluation map going from the set of polynomials of degree less than or equal to k minus 1 to the set of n tuples of elements of FQ. Okay. And it is very clear that this is a linear map. If f goes to CF, g goes to CG, f plus g will go to CF plus CG. Okay. Just because the substitution map is a linear map. Okay. So in other words, these n tuples of evaluations of polynomials of degree less than k at some fixed n points in FQ will constitute a subspace of FQ to the power n. So this is living inside FQ to the power n. Okay. Question: what is the dimension of this? Okay. By the way, the only requirement here is that this A1, A2, An should be distinct elements of FQ, for which your Q should be larger than or equal to n. So what is the dimension of this? Anybody? It's written here.
Q raised to n.
Sorry, Q raised to n? 2 raised to n? No, what did you say? No, I want to ask the vector space dimension of C. Okay. Let me ask you this. Suppose I look at this space of polynomials of degree less than or equal to k minus 1. Okay, that's a vector space. What is the dimension of this vector space? Can somebody tell me?
K. Q raised to k.
No, Q raised to k will be cardinality. Will be k, right?
Dimension is k.
Because 1 x square x to the k minus 1 would be a basis. Correct? Yeah. Now, if you can show, for example, that this evaluation map is injective, then the dimension of the image, which is C, will also be k, isn't it?
Yes.
And one way of showing this map is injective is that that word kernel is 0. That means if something goes to 0, then it must be the 0 polynomial. What does it mean to say that a polynomial fx is mapped to a 0 tuple? It means f of a1 is 0, f of a2 is 0, and f of an is 0, right? What does that mean? That means I have this polynomial of degree less than or equal to k minus 1, and it has n distinct roots, right? But what is n? N was q is greater than or equal to n, and n is greater than or equal to k. So, so if it has n distinct roots, that means it has k or more roots. But what is the degree? Degree is k minus 1 or less. So if I have a polynomial of degree k minus 1 or less, it cannot have more than k roots unless what? Unless it's the 0 polynomial, right?
Yes, sir.
So that shows that only polynomial which is mapped to the 0 tuple is the 0 polynomial. In other words, this map is not only linear, but it is injective, and therefore dimension of C is exactly equal to k. So you get yourself a code of length n and dimension k. So it's an nkq code. Okay. Now let us try to understand what would be the minimum distance of this code. Now, what is the minimum distance? Okay, maybe I use a different color. The minimum distance of this code would be, let's see, d of C. That would be the minimum of the Hamming weight of CF, right? CF, or I can even vary F. Let's say degree of F is less than K and F not equal to 0. Okay. So in other words, what is that? Now, what is the Hamming weight of f? So you look at this polynomial again. You look at this CF again. What would be the Hamming weight of that? Are you able to see my slides now?
Yeah, please.
Okay. Okay, there's a slight time lag between when I highlight something and it gets highlighted back here. Just a moment. By the way, how much time do I have?
Maybe you can wind up in 5 minutes or so.
Okay, very good. I'll do that.
Please.
I'll do that. Yeah. No problem. So, so let us try to understand what is the minimum distance of this. Okay. So what is the Hamming weight here? The Hamming weight is going to be, so look, this one. The Hamming weight is going to be weight of CF is going to be the number of positions in which the CF has a 0 coordinate. So that means it is, so total number of position is n minus the number of I, such that f of ai is 0. Right? That's going to be the weight. Now f is what? F is a non-zero polynomial of degree less than or equal to k minus 1. And so it's like n minus the number of roots of f among a1 to an. But f is if it's a non-zero polynomial of degree k minus 1, we learn in school, then it has at most k minus 1 roots, right? So so this number is going to be less than or equal to k minus 1, whatever it is. And because it comes with a minus sign there, this n minus that would be greater than or equal to n minus k minus 1. So n minus k minus 1, which is n minus k plus 1. Okay. So in other words, the Hamming weight of every non-zero code word is greater than or equal to n minus k plus 1. Moreover, it is very easy to write down as something of Hamming weight n minus k plus 1. How do I do that? I just pick up k minus 1 of the AIs, a1, a2, ak minus 1, for example. And I simply look at the polynomial x minus a1 into x minus a2 into x minus ak minus 1. This is exactly k minus 1 roots among a1 to an. And therefore, the Hamming weight of the corresponding code word is n minus k plus 1. In other words, what I've just proved is that the minimum of Hamming weights of non-zero code word is precisely n minus k plus 1. In other words, this is a MDS code. Remember, this n minus k plus 1 was always an upper bound. So this is a code of length n, dimension k, and that's a very beautiful class of codes which sort of comes from algebra. It's called the Reed-Solomon code. We know a lot about this code, including something called decoding and so on and so forth. So let me just mention in passing that these are exactly the sort of codes which are used to correct errors in lots of storage devices like compact discs, DVDs, Blu-ray discs. Okay, you can, for example, look at the Wikipedia article. Just Google on Reed-Solomon error correction, and you will get a lot of technical information if you're interested. I don't have too much time, but I want to mention just one more class of codes. Okay, I have this thing about spear packing. Okay, so let me maybe if I have just 5 minutes, I may not have time to discuss that. This is related to various bounds which are important in coding theory. There is something, the simplest of them, that's called the spear packing bound, and there is something called spear, and there are codes which meet that spear packing bound. They are called perfect codes. And what I'm hoping to show here is that this Hamming code, which I introduced earlier, is a nice example of a perfect code. And this is it's a rare class of codes which are perfect. You can ask me questions. I can come back to this. I don't want to take more time than what I'm allotted. So this is I mean, I have remarked here that like in real life, perfection is rare. That means it's rare to find codes which are perfect codes. So Hamming codes are examples of them. There is something other class of code called Gole codes which come from geometry and so on, finite geometry. and group theory, that they're also perfect, but these are just about the only known examples of perfect codes. Then there is something called a sphere covering. Sorry. Which are okay, which lead to a very nice set of asymptotic bounds. Okay, let me end by introducing to you this other important class of code, Reed-Muller code. I mean, I talked about Reed-Solomon code. What was Reed-Solomon code? This Reed-Solomon. Oh, sorry. Reed-Solomon I constructed when I had q greater than or equal to n greater than or equal to k. And if you want your k to be rather large, the one drawback is there that q will have to be pretty large. If you want a code of pretty big size, because size of a code of dimension k will be q to the power k, q will have to be much larger. So if k is like 1 million, your alphabet set should be of order million or more. Okay. But what if you just want to use with the binary field and you still want to get a good, nice class of codes? So that's the Reed-Muller code is one of the classical examples of that. So, so what you do there is you take any q, you don't put any condition like q greater than or equal to n. But instead of polynomials in one variable of degree, let's say less than or equal to k minus 1, what you do is you look at polynomials in more than one variables. Say polynomials in m variables of degree less than or equal to some fixed non-negative integer nu. So look at polynomials in m variables of degree less than or equal to nu. And then what you do is you have your m-dimensional vector space fq to the power m, set of m tuples. How many elements does it have? It has q to the power m elements. You write them down, p1, p2, p3, p sub q to the power m. And then what you do is you take a polynomial f in this of degree less than or equal to nu, and you simply evaluate it at each point of the space fq to the power m. This space, okay? And the image of this evaluation map is easily seen to be linear, would be a code of length q to the power m, and that's what is called a Reed-Muller, query Reed-Muller code. Okay, and let me. So as I said already, it's easily seen to be a code of length q to the power m. What about the dimension here? As far as the dimension is concerned, in general, that evaluation map is not injective. In some special cases, it is injective. When it is injective, the dimension of the now space of polynomials in m variables of degree less than or equal to some fixed number nu. It's an easy exercise combinatorially to show that this is given by the binomial coefficient m plus nu choose nu. Okay. So for example, if m were equal to 1 and nu were equal to k minus 1, this is nu plus 1 choose nu, or nu plus 1 choose 1, it is nu plus 1. So if nu is k minus 1, that is k, just like in the Reed-Solomon case. But in general, it is given by this formula. Except that in general, the map may not be injective, and then the dimension is given by a somewhat, okay, so you have to, dimension is given by a somewhat complicated formula. It turns out the map is injective if nu is less than q. Okay. Then the dimension of the Reed-Muller code is given by this binomial coefficient. But if that is not the case, then you have to do a little bit of algebra to show that the dimension is given by a somewhat involved formula like this here. This equation 2. Okay, I don't have time to explain this. It's not difficult. If somebody is interested, I can explain to them that. And I just want to sort of say what kind of thing will go into finding the minimum distance of this Reed-Muller code in general. So, okay, this is a proof. Never mind that. So there is a classical inequality which was proved by Oystein-Ore, which is an analog of what is the maximum number of zero that a polynomial in m variables of degree at most nu can have in fq to the power m, and that bound is given by nu times q to the power m minus 1. This is an interesting bound if nu is less than q. That's exactly the case when the code as dimension m plus new choose new. So, so for example, if m were equal to 1, you're saying a polynomial in one variable of degree nu has at most new roots. But this is like a generalization of that to polynomials in several variables, except over finite fields. Okay, so once you get that, then it is easy to see that when the minimum distance will be given by q to the m minus nu q to the m minus 1, so minimum distance of the Reed-Miller code of order nu and length q to the m, if nu is less than q. But if nu is not less than q, it's a more challenging problem, which has been answered by various mathematicians. So that this is what I just said: q to the m minus nu q to the m minus 1. And in the general case, you have to do some work and get the formula for minimum distance. You can even understand the duals of these codes, which are also Reed-Miller codes, and you can even understand the generalized Hamming weights, etc. And you're already close to some relatively recent research papers in this area. Okay, just want to make one remark. If you open Van Lin's book, you will see that Reed-Miller codes are exactly the codes which were used to send data from the Mariner satellite, which went to Mars, because they took various images, and now they want to send that images across digitally back to Earth, and it was very likely that they could get corrupted. And what they used was actually a Reed-Miller code on a larger alphabet set than of size 2. So these codes are not only mathematically interesting, but they have also been applied in practice and continue to be applied. So I think with that, let me stop here, and I thank you for your attention. Okay, there seem to be.
Yeah. So would you like to, anybody would like to share any comments, questions? Already, Ajit Iqbal Singh has already shared some comments about.
Iqbal Singh is here. Okay.
Yeah.
Oh yeah.
About MDS codes, but others.
Yes. Yeah.
Professor Ajit Iqbal Singh, would you like to say something more? Or the link is good enough? In the meantime, anybody else would like to ask a question or say something? Please unmute your mic and say.
Yeah. Yeah, Professor.
Let me just stop you for a minute and say that please, others can fill up the feedback form in the meantime. So Anindya, please go ahead.
Yeah. Thank you, Professor, for the wonderful talk. And so how is about the decoding for this RS code?
Yeah, so decoding for RS code is possible. It will need maybe 2 or 3 lectures to explain that. If you can write an email to me, I can send you some references.
And another generic question: that what is the difference between coding theory and cryptography?
Okay, good question. So coding theory and cryptography, sometimes they are spoken in the same breath. So they are and they are not related areas. See, roughly speaking, the goal of coding theory, as I explained to you, is to be able to detect and correct errors when they occur in digital transmission. So in other words, whereas in cryptography, the genesis of cryptography sort of comes by you have some data and you are sending it again across this cyberspace, but it is some important data, maybe like your credit card number or something like that, and you don't want that data to be hacked by somebody, so you sort of want to make it cryptic. So therefore, instead of sending the same data, you send it in some cryptic form in such a way that the receiver is able to decrypt that data. But if some intermediary, some hacker were to look at that, then he or she may not really get access to that. Let me just give you a very, very simple example of what can happen in cryptography. This is coming from what are called stream ciphers. So let's say you take your credit card number, which is typically a 16-digit integer. Okay. By the way, these are also not random integers. if you try to change some digits somewhere and pass it off as your credit card number, I'm sure system will mark it as wrong. So there are some number theoretic tests, but that's besides the point. So let's say you're sending your credit card number. Your 16-digit credit card number is converted to a sort of longer bit sequence in the binary form. And what you do is that instead of sending that number, you just add to it some randomly generated. So your, let's say your credit card number becomes a string of zeros and ones of length 100. Okay, so let me call it M. And to M, you can add some another 100 length 100 binary number, say K. And you instead of sending M, you send M plus K. Now this M plus K, of course, will completely distort what M was originally. Whatever was 0 may have become 1. What was 1 will become 0. So if somebody were to hack that, they would see M plus K. Okay, but now the system which generated M plus K, the correct receiver, he knows that such a key was generated. So all the receiver has to do is he receives this M plus K and you just add. So you to M plus K, you just once again you add plus K. And because binary arithmetic being such that K plus K will be 2K, which is 0, you get back your M. That's one simple technique which is sometimes used. This is called stream cipher. It is, it uses what are called linear feedback LFSRs. Exactly. But there are variants of these LFSR. Correct. There are word-oriented LFSR and so on and so forth, which make this more thing. So the point is that the goals of cryptography are there you want to not make it easy to decode the message, but to make it somewhat difficult to decipher the message. But the receiver should be able to decipher it anyway correctly. And these are typically done with the messages of smaller, bit length, smaller whereas in coding theory, you're not so worried if somebody else steals your data which is coming from Mars. You really want that data in as uncorrupted form as possible. So, but you seem to know more about cryptography. So, the people these days there is something called post-quantum cryptography. People fear, what if there are quantum computers? And then they can break many of the currently used crypto systems, RSA and so on. So there are NIS post-quantum candidates for various post-quantum cryptography. One of the candidates is code-based cryptography.
Code-based cryptography. MAC-Alice crypto system is there.
Exactly.
And classical MAC-Alice. And it is not shortlisted in the final.
That is right. So in that way, coding theory and cryptography are also related. But
and lattice-based cryptography is also inspired from the coding theory tools.
Correct. And lattice theory also has connections to coding theory. Lattice and that is true.
This learning with errors, all these stuff.
That is true. But in one lecture, I can only tell so many.
Yeah.
Already, what I will be able to say, I did not get to that, but that's okay.
I think we'd like.
The goal is to get
anybody else would like to ask something? Anindya, you would like to email with Professor Ghorpade and get more interactions with you?
Yes, sir. Thank you.
Yeah, sure. Anybody else would like to say something, please? Yeah, and others, I hopefully have filled up the feedback form also. So Professor Ghorpade's email, would you like to put your email in the chat box?
Yeah, sure.
Yeah.
It's sudhir@gmail.com.
Yeah,
I'm typing.
Simple as.
Yeah, that's very simple.
Yeah.
Just one word, no space.
Yeah. So I encourage you to interact and
as I said, you can find my notes on coding theory on my homepage if you sort of click your way around. And
just a curiosity, Sudhir.
Yeah.
Do you think QR codes are they anywhere near algebraic coding, or is it just a question? Okay.
Yeah. QR codes. In fact, they also use something like Reed Solomon.
Okay.
But I mean, another simplest form, maybe I should have said this in the beginning. Another very, very simple type of error correcting code you see when you open any book that you take. It has what is called an ISBN number.
All right.
And this ISBN number has a sort of one error detecting code built into it. So you can sort of imagine a library clerk typing in the ISBN numbers of if they have some built-in encoding in such a way that so if somebody makes one mistake in the ISBN code, the machine can sort of say that, look, this doesn't look correct. You may want to correct it. It's just a 13-bit thing. I mean, there is 11-digit and 13-digit ISBN. So yeah, I mean, coding theory is really everywhere.
Yeah, and it's really a wonder that something which Galois would have never thought of field theory getting into this kind of application.
Yeah, that's right.
These are wonders of mathematics.
In fact, there are aspects of coding theory where all kinds of deep mathematics comes into picture. There's something called Gopa codes, and people used what are called elliptic modular curves to construct a very efficient class of Gopa codes. The names that come to mind are Ihara and Fassmann-Vladutzing, which beat the so-called Gilbert-Marshall bound. So there are these so-called geometric codes. Yeah.
This is a stage probably where you can say the boundaries between pure and applied over the time they get mixed. And see, I mean, we should call it only mathematics.
Exactly. Philosophically, I don't believe there is any such thing as pure mathematics or any such thing as applied mathematics. So what is pure today may get applied tomorrow.
Yeah, sure. So, and we are seeing many examples of that getting it actually.
Yeah.
So let me thank you once again, Sudhir, for taking time off and enlightening us about the codes. I was trying to generate a code for saying thank you. I couldn't do it.
That's okay.
Yeah, I tried QR code, but that only does for websites kind of a thing. So it's okay. Thank you very much. It was a pleasure listening to you. And I hope everybody has... there was somebody saying that will the PDFs of the slides be available? I don't know. I think you should.
Well, I can email it. I can email it to you, Rana, and if you want to available on the website, that's fine with me.
Yeah, we can think of that. That's one possibility. Or they can directly write to those who are interested. Can write directly. That will
absolutely
show your interest also that you are really interested in having the PDFs. Yeah.
Sure.
Thank you, Sudhir, once again. And
okay, thank you.
We hope that sometime later again we'll rope you in. Thank you very much.
Yeah, thank
you. Thank you everybody for coming for that.
And happy Independence Day, everybody.
Yeah, happy Independence Day. Right. Today is
Happy Independence Day.
But I mean, we are supposed to celebrate from today itself.
Yeah, Tiranga Mahotsav starts today itself. So happy Independence Day. Take care. Be safe. Thank you, Sudhir, once again. Thank you, everybody.
Thank you.
Bye, sir. Thank you.
Bye. Samya.
Bye, sir. Bye.
Bye, Samya.
Bye. Bye, Professor Ajit Iqbal Singh. Thanks for being here.
Thank you.